from JWST reveals something far more extraordinary and potentially disturbing. The object's prismatic, crystal-like structure, its impossible material composition, and its eerily perfect rotation are raising questions that challenge our understanding of natural space objects. Some of the data is so unusual that scientists are quietly discussing possibilities they never thought they'd have to consider. In 2017, astronomers around the world were stunned when telescopes in Hawaii detected something completely unprecedented. A small, fast-moving object shot through our solar system, but unlike anything ever catalogued before, its trajectory proved it didn't originate here. It came from far beyond, from the vast interstellar void. This visitor was given the name Oumuamua, meaning a messenger from afar arriving first in Hawaiian. For years, scientists struggled to understand what it truly was. The only tools available back then were limited: ground-based telescopes, faint light curves, and infrared readings that provided only the vaguest outline. The images were blurry, indirect, and left more questions than answers. Was it a comet without a tail? A strange asteroid? Or something entirely new? For half a decade, the mystery deepened. Countless theories emerged, from exotic natural formation to bold suggestions that Oumuamua could be artificial in origin. But there was one huge problem. No one had ever seen it clearly. Humanity had no true picture of this visitor until now. Enter the James Webb Space Telescope, the most advanced eye humanity has ever placed in space. Stationed a million miles from Earth, Webb's instruments are designed to peer deeper into the universe than anything before it. But when scientists turned its gaze not at distant galaxies, but at Oumuamua, history was made. For the very first time, we weren't looking at guesses, sketches, or artist renderings. We had a real, high-resolution image of an interstellar object passing through our neighborhood. What Webb revealed was breathtaking. No longer just a speck of light, Oumuamua appeared in full detail. Its surface, its shape, its very character came into view. This wasn't just science. It was a historic moment, the first time humanity captured the face of a visitor from another star system. The implications of that single image cannot be overstated. It marked the end of speculation based only on shadows and signals, and the beginning of direct observation. For astronomy, it was like stepping into a new era overnight. The James Webb image doesn't just show us an object. It shows us that we are not isolated. Our solar system is not a sealed-off bubble. Matter, fragments, and perhaps even the seeds of life itself move between the stars, and Oumuamua is proof of that journey. What Webb delivered was not simply a picture, but a window into the vast interstellar network that connects us to distant worlds. When Oumuamua was first discovered in 2017, the limited data made astronomers think it was elongated, a strange, cigar-shaped rock tumbling end over end through the solar system. This unusual assumption captured the public imagination. After all, nothing in our own asteroid belt or Kuiper belt looked quite like that. It was long, thin, and unlike the round or potato-shaped worlds we were used to seeing. For years, the cigar image became the face of Oumuamua, endlessly reproduced in documentaries, articles, and speculation. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like so we know to keep uncovering them. But now, thanks to the James Webb Space Telescope, that picture has completely changed. Webb's powerful instruments have given us the most detailed look yet, and what it shows is far stranger than anyone could have imagined. Instead of a smooth, elongated rock, Oumuamua appears as a prismatic, faceted structure. Imagine a shard of crystal or an angular fragment of glass with flat planes that catch and reflect light in sharp, geometric ways. That is what Webb has revealed. This geometry is deeply unusual. Objects in space rarely form with flat surfaces or sharp angles. Natural processes tend to create curves, spheres, ellipses, and irregular lumps worn down by collisions or erosion. But Oumuamua defies those expectations. Its sides seem to meet in edges, its surfaces gleam in facets, and it looks more like something fractured or carved than something naturally rounded. To some scientists, this prismatic shape hints at an origin very different from a normal asteroid or comet. Even more mysterious, these angular planes reflect light in an odd, almost crystalline manner. As Oumuamua rotates, the brightness we see doesn't match what a typical rocky or icy body would show. The reflective qualities are inconsistent with a simple hunk of stone drifting through space. Instead, they suggest materials that interact with light in unusual ways, perhaps metals, exotic ices, or even layered composites we don't fully understand. This discovery reignites a profound question. Could Oumuamua be a fragment of something larger? Perhaps it once belonged to a shattered planet, where violent collisions created crystalline shards that drifted into interstellar space. Or perhaps it is the remnant of some completely unknown cosmic process, one we've never seen before. And for some, the clean lines and angular form fuel a far bolder speculation that this geometry could be the hallmark of intentional design, as if this shard was once part of a structure, crafted rather than born. What makes this all the more fascinating is how it challenges our categories. We've always divided objects into neat boxes: comets, asteroids, dwarf planets. But Oumuamua doesn't fit. Its prismatic body is a new entry in the cosmic catalog, a shape that forces scientists to ask whether we've underestimated the diversity of interstellar objects, or whether we've just glimpsed something beyond the natural. If the shape of Oumuamua was already shocking, what James Webb discovered on its surface was even more bewildering. Using its powerful infrared and spectrographic instruments, Webb didn't just capture light bouncing off the object. It broke that light down into its chemical fingerprints. These spectral signatures revealed exactly what Oumuamua is made of, and the results were unlike anything we've ever seen in a natural interstellar body. The data showed a bizarre patchwork of materials spread across its surface. Certain regions reflected like polished metal, shining with the sharp brightness of reflective compounds and frozen ices. Yet just next to those gleaming surfaces were zones that seemed to swallow light, carbon-rich and almost pitch black, absorbing nearly everything that touched them. It was a striking contrast, as if the object were wearing two completely different faces at once. Even more puzzling, Webb picked up iridescent areas, surfaces that shimmered in changing colors, depending on the angle of the light. This phenomenon is rare in space. Iridescence usually requires layered or crystalline materials arranged in a precise way, like the shifting sheen of an opal or the rainbow glint on a soap bubble. For something drifting alone between the stars, that kind of surface effect is highly unexpected. And then there were the ices. Not ordinary frozen water, but exotic ices formed of molecules that, under normal circumstances, shouldn't be found together. Some appeared to be the kinds of volatile compounds we'd expect only in the deep freeze of interstellar space. Others hinted at chemistry, more complex than any comet we've studied before. This strange mix suggested that Oumuamua had either formed in an environment radically different from our solar system, or that it had undergone a unique transformation during its long journey across the galaxy. The real mystery lies in how these contradictory materials coexist. Metals and reflective ices usually don't survive in direct contact with carbon-rich absorbers. Under normal cosmic conditions, one would erode or consume the other. Yet on Oumuamua, they sit side by side, preserved in stark contrast, as if protected by some unusual process. Scientists admit that this chemical patchwork doesn't fit our current understanding of planetary geology or cometary evolution. What this means is that Oumuamua carries within it a record of unknown cosmic chemistry. It may be a fragment, torn from a differentiated world, where heat, pressure, and strange atmospheres gave rise to compounds we've never observed elsewhere. Or it may have collected these unusual materials during its passage through different star systems, like a traveler gathering scars from each environment it crossed. For some researchers, though, the combination is simply too odd to dismiss. They've suggested that such juxtapositions might not be entirely natural. A layered patchwork surface of reflective and absorptive materials could serve a purpose, regulating heat, protecting the core, or even controlling the way the object interacts with radiation. While most scientists are cautious, the unusual chemistry of Oumuamua's skin keeps the door open to a possibility we can't ignore, that this might be more than just a rock. When astronomers first tracked Oumuamua in 2017, one of the biggest surprises was its rotation. Most small objects in space, asteroids, comets, even icy fragments, tumble in a chaotic dance. They spin irregularly, often wobbling due to uneven shapes and past collisions. Think of a stone thrown into the air, rolling end over end, its movement unpredictable. But Oumuamua broke that pattern. What James Webb confirmed is that Oumuamua does not tumble at all. Instead, it rotates with remarkable stability, completing one full spin every 8.3 hours. Its rotation is steady, controlled, and consistent, more like a balanced gyroscope than a drifting shard. That stability is unusual for something of its size, especially for an object traveling so far and so fast through interstellar space. This behavior tells scientists something critical. Oumuamua must possess strong internal cohesion. In simple terms, it's held together tightly. Many small space rocks are what we call rubble piles, loose clusters of debris barely bound by gravity. If you spun one of those too fast, it would fling itself apart. Yet Oumuamua holds together as a single solid body. Its rotation speed is exactly within the safe range for a firmly bonded structure, suggesting its insides are not loose rubble, but chemically or structurally solid. The question then becomes, what kind of object behaves this way? A naturally fractured shard could theoretically be this solid, but Oumuamua's strength and precision of spin hint at something more unusual. If it were simply a chunk of ice or rock, we would expect some wobble. Irregularities in density usually throw objects off balance. But Webb's observations reveal a rotation that looks engineered, too stable, too perfect to be the result of random cosmic chance. There's also another layer of mystery. Objects traveling between star systems are exposed to countless forces, gravitational pulls, collisions with cosmic dust, even the gentle push of radiation. Over millions or even billions of years, these forces usually disrupt an object's spin, creating wobbles and instabilities. Yet Oumuamua's rotation is smooth, as if it has resisted those influences, or as if something has preserved its balance. This leads to two possibilities. Either Oumuamua is made of an exotic material that gives it extraordinary strength and resilience, unlike any asteroid or comet we know of. Or, more intriguingly, it was once part of a larger, more ordered structure, something that required stability for a purpose. Some scientists have even compared its spin to that of spacecraft, which are designed to rotate or stabilize for navigation. The fact remains, Oumuamua doesn't behave like a loose fragment of rock. It behaves like a cohesive, unified body. And that simple observation, a spin every 8.3 hours, opens up questions far bigger than the object itself. How did it form? What forces kept it so stable? And most importantly, is this precision just a cosmic coincidence or a subtle clue to something more? If Oumuamua's shape, surface, and spin were not strange enough, the James Webb Space Telescope uncovered yet another puzzle, one hidden in how the object handles heat. In space, the rules of thermal behavior are straightforward. When sunlight strikes a small rock or icy body, it warms up quickly. When that sunlight fades, the heat radiates away just as quickly. But Oumuamua doesn't follow those rules. Webb's TUFI's Instruments measured its thermal signature and found that Oumuamua heats up and cools down far more slowly than expected. When it passes into sunlight, it doesn't immediately glow with heat as a normal rock or comet would. And when it moves out of the light, it holds onto that warmth much longer than physics predicts. It's as if Oumuamua carries an invisible thermal blanket, regulating its temperature in ways no ordinary interstellar fragment should. So what could explain this? One possibility is that Oumuamua has insulating layers. Imagine a shell of material, perhaps foamy or fibrous in structure, that slows the transfer of heat from its surface to its interior. Some comets in our solar system show a hint of this effect, but nothing nearly this extreme. For Oumuamua, the insulation would have to be far more efficient, hinting at materials we don't usually associate with natural space debris. Another possibility is that Oumuamua is porous, filled with empty pockets like a sponge. If its interior is riddled with voids, heat would travel through it more slowly, creating the delayed thermal response Webb detected. But the level of porosity required here is far beyond what scientists typically expect. It would mean Oumuamua's structure is not just irregular, it's radically different from anything in our catalog of asteroids and comets. And then there's the most intriguing possibility of all, that Oumuamua might actually be hollow. A hollow interior would not only change the way it absorbs and radiates heat, but would also explain some of its other unusual properties, like its strong cohesion and stable spin. Hollow objects in space are extraordinarily rare in nature, if they exist at all. Yet in engineering, hollow designs are common. They reduce weight, regulate temperature, and preserve structure. This hollow possibility is where speculation begins to rise. Could Oumuamua be the remnant of something artificial, perhaps a fragment of a larger vessel, or even a discarded shell drifting between the stars? To be clear, there is no conclusive evidence of that. But the thermal mystery forces scientists to consider scenarios that don't fit comfortably within natural explanations. What's certain is this: Oumuamua doesn't behave like a rock, an ice ball, or a comet. It absorbs heat like nothing we've seen, and it holds onto it as though it were designed to. And whether the cause is insulation, porosity, or a hollow heart, each answer pushes Oumuamua deeper into the realm of the extraordinary. The James Webb Space Telescope also uncovered something that pushes Oumuamua's mystery to an entirely new level. When Webb focused its powerful instruments on the object, it didn't just capture its strange surface. It revealed that Oumuamua's skin is divided into sharply distinct zones, each with its own unique spectral fingerprint. In astronomy, spectral fingerprints are everything. They tell us what a surface is made of, how it formed, and sometimes even where it came from. Normally, when we look at comets or asteroids, their spectral signatures are messy blends. Dust, ice, and rock are scattered randomly, creating surfaces that are chaotic and mixed. But Oumuamua doesn't look like that. Instead, its surface is neatly segmented, with clear boundaries between regions. One area shines with reflective, metallic compounds. Another absorbs nearly all light with carbon-rich chemistry. Others shimmer with iridescent materials or exotic ices. Each of these zones seems to belong to a different chapter of the object's history. This kind of separation is rare. It suggests something profound. Oumuamua isn't just a random shard. It is a piece of something larger, something that had already undergone differentiation. Differentiation happens when a planetary body grows large enough that heat and pressure separate its materials into distinct layers. Heavy metals sinking to the core, lighter silicates rising to the surface, volatile compounds trapped in outer shells. It's the process that shaped Earth, Mars, and many moons in our solar system. For Oumuamua to display this kind of differentiated structure, it must once have belonged to a parent body large enough to sustain that process. That means Oumuamua might be a fragment, torn from a planet, a moon, or a protoplanet that never fully formed. Some researchers even suggest it could have come from a planet destroyed during the violent birth or death of another star system. Imagine a world shattered by gravitational chaos, its fragments scattered into interstellar space, drifting for millions of years until one shard finally found its way to us. This is more than just speculation. The sharply divided zones that Webb detected don't happen by accident. They tell us Oumuamua is a survivor of a catastrophic event, carrying with it the chemical memory of a lost world. If true, then Oumuamua isn't simply the first interstellar object we've observed. It may be the first physical evidence of a destroyed alien planet to ever enter our solar system, and that thought changes everything. For the first time, we may be holding clues not just about other star systems, but about the life cycles of their worlds, their births, their deaths, and the fragments they leave behind. Oumuamua, in this sense, is not just a rock. It is a messenger from a planetary graveyard, silently carrying the scars of a world that no longer exists. Perhaps one of the strangest revelations from the James Webb Space Telescope came not from what Oumuamua had on its surface, but from what it didn't. After a journey spanning what could be millions of years through interstellar space, scientists expected Oumuamua to be covered in a fine veil of dust. Space between the stars isn't empty. Microscopic grains drift endlessly, and over vast stretches of time, they cling to any object passing through. Most asteroids and comets we've studied carry that dusty coating, a kind of cosmic aging that tells us they've been traveling for eons. But when Webb examined Oumuamua in detail, it saw something different. Its exterior was strangely clean. The reflective zones Webb mapped were sharper, brighter, and more exposed than they should have been. The usual soot of interstellar travel just wasn't there. It was as though Oumuamua had been scrubbed, revealing bare surfaces that should have long since been hidden under layers of cosmic dust. So what could explain this? The first idea scientists considered was natural cleansing. One possibility is sublimation, the process by which certain ices turn directly into gas when heated by starlight. If Oumuamua carried exotic ices beneath its surface, they could have vented small bursts of gas over time, sweeping away accumulated dust in the process. Another explanation could be spin shedding. Because Oumuamua rotates with such steady precision, centrifugal force might slowly fling dust away from its surface, leaving it remarkably clean compared to other bodies. Yet, even these natural explanations struggle to account for just how pristine the object appears. The level of cleanliness suggests something more continuous, something more active, and this is where controversy begins. Some researchers have suggested that the absence of dust could point toward active mechanisms. In other words, Oumuamua might not only passively shed dust, it might be maintaining its exterior in a way we don't yet understand. That idea has sparked debates in the scientific community. Could Oumuamua, against all odds, be equipped with some property, natural or otherwise, that keeps its surface clear, reflective, and sharp? Is it possible that what we're looking at is not just a fragment of rock or ice, but something with surfaces intentionally kept free of debris? To be clear, there's no proof of artificial maintenance here, but the fact remains undeniable. Oumuamua's surface looks far too clean for an interstellar traveler. Whether that cleanliness comes from exotic natural processes we've never witnessed before, or from something more deliberate, it deepens the mystery of this object. In the end, the dust-free exterior may be one of the strangest clues yet. It's as if Oumuamua wants to be seen clearly, as though the cosmos itself has polished this shard before sending it into our solar system. And that simple fact leaves us with a haunting question. Why does this interstellar visitor look so different from everything else drifting through the void? When the James Webb Space Telescope turned its attention to Oumuamua, it didn't just reveal surface chemistry and structure. It also uncovered something far stranger: the way this object interacts with light itself. Webb's instruments picked up unusual reflections, behaving in ways scientists call anisotropic. In simple terms, the light bouncing off Oumuamua didn't scatter evenly the way it does from rocks, comets, or asteroids we know. Instead, it flashed back in irregular, directional pattern, almost as if parts of the object were angled like mirrors. This might sound subtle, but in astrophysics, details like this matter. They hint that Oumuamua's surfaces may not be random or rugged, but instead are flat, faceted, and arranged in ways that can reflect light with precision. That alone sets it apart from the countless natural fragments drifting through the cosmos. Even more curious is the object's mass-to-surface ratio. By studying how Oumuamua moves under the influence of solar radiation, scientists realized it behaves as though it's far thinner and lighter than an ordinary asteroid or comet of its size. Its body doesn't act like a dense rock. Instead, it resembles something lightweight, possibly sheet-like, the kind of proportions you'd expect from an ultra-thin structure, not a solid space boulder. This is where speculation heats up, because what in nature could create an interstellar shard with such unusual proportions? One comparison that keeps surfacing is the idea of a solar sail. A solar sail is a concept humans have already begun testing, a broad, thin sheet designed to catch photons, tiny particles of light, and use their momentum for propulsion. For Oumuamua to have a low mass-to-surface ratio that allows sunlight itself to push it, even slightly, raises eyebrows. It's exactly the kind of property you'd engineer if you were building a craft meant to drift between the stars. Now, most scientists remain cautious. They lean toward natural explanations. Perhaps Oumuamua is a fragment of exotic ices, a wafer-thin sliver peeled away during a planetary collision, or some other natural phenomenon we've never encountered before. But even those theories struggle to explain its reflective behavior, its lightness, and the way it moved as it passed through the solar system. And so the debate refuses to die. Could Oumuamua be natural, yet unlike anything we've ever cataloged? Or is it something far more extraordinary, a relic of technology not our own, sent adrift in the interstellar sea? Webb's data doesn't provide a final answer, but it undeniably keeps the door open. Whether a natural shard shaped by exotic physics, or the wreckage, or even a functioning remnant of advanced engineering, Oumuamua forces us to expand the boundaries of what we think is possible. And that's the greatest gift it leaves us. A reminder that the universe may hold not only mysteries of nature, but also, perhaps, the faint traces of intelligence far older and wiser than our own. Beyond its unusual shape, surface, and motion, Oumuamua may hold clues to one of the most profound questions humanity can ask: how life begins and spreads across the cosmos. Spectral analysis from the James Webb Space Telescope revealed that Oumuamua contains complex organic molecules, the chemical building blocks that, under the right conditions, can lead to life. These aren't simple carbon compounds. They're intricate structures capable of forming amino acids, sugars, and other prebiotic ingredients. What makes this even more fascinating is how Oumuamua's structure seems to protect these fragile molecules. Its dense faceted surface, combined with possible insulating layers or even hollow regions, could shield organics from harsh radiation and extreme temperatures during interstellar travel. In other words, it's not just a random rock carrying chemicals. It's a remarkably resilient vessel capable of transporting the seeds of life across unimaginable distances. This brings us to a concept called panspermia. Panspermia is the hypothesis that life, or at least prebiotic compounds, can travel between star systems on comets, asteroids, or interstellar fragments. It suggests that life on Earth might not have originated here at all. It could have been delivered from another corner of the galaxy, hitching a ride on a celestial body like Oumuamua. The implications are staggering. If Oumuamua truly carries prebiotic molecules protected within its unusual structure, it may represent a direct example of life's potential to spread between stars. Each interstellar visitor becomes not just a scientific curiosity, but a messenger of cosmic biology, capable of bridging solar systems with the raw ingredients for life. Even more tantalizing is the idea that Oumuamua might have been doing this for millions, perhaps billions of years. Its journey across the galaxy could have exposed it to countless star systems, picking up and preserving organic material along the way. It's a traveling ark, silently moving through the void, possibly connecting distant worlds through the chemistry of life itself. In essence, Oumuamua challenges more than our understanding of physics or planetary science. It forces us to consider the universe as a living, dynamic system where the building blocks of life might not be confined to a single planet, but can travel vast interstellar distances, seeding potential in places we have yet to imagine. Oumuamua is not just another space rock passing through our solar system. Its discovery has sent shockwaves through astronomy, planetary science, and even philosophy. Every new detail, from its unusual shape and faceted surfaces to its dust-free exterior and exotic chemistry, challenges the models we've relied on for decades. Scientists are now forced to rethink how planets form, how debris from distant star systems travels, and how interstellar objects should even be classified. Before Oumuamua, we imagined interstellar visitors as small, random, and largely unremarkable fragments. Now we see that they can be structurally complex, chemically diverse, and potentially carry prebiotic molecules across galaxies. This transforms our understanding of galactic material exchange, suggesting that stars and planetary systems are not isolated islands, but participants in a vast network of cosmic recycling. Materials, and possibly the seeds of life itself, move between systems, shaping the evolution of planets in ways we've only begun to grasp. The implications reach beyond science. Oumuamua inspires a new generation of exploration. Missions could be designed to intercept similar visitors, to sample their surfaces, or to even deploy small probes that travel with them. Future telescope surveys may focus on finding more of these interstellar objects, mapping their trajectories, and decoding their chemical and structural signatures. Each discovery will expand our understanding of the galaxy and our place within it. But the impact is not only technological or scientific. Oumuamua invites a cultural and philosophical reflection. It reminds humanity that we are part of a dynamic, interconnected cosmos. Objects born around distant stars can visit our solar system, carrying the history, chemistry, and perhaps even the biological potential of alien worlds. It challenges our sense of permanence, urging us to see the universe not as a static backdrop, but as a vast, ever-changing tapestry in which we are a small, yet aware thread. In the end,